Okay, so in this unit, we're going to be very quickly, right, essentially today, I'm going to be introducing you to, again, the quantum mechanical atom and its properties and the way we actually look at the atom. I'm going to be introducing you to something called orbitals, all right? And you might think that that's something you've already heard, but in terms of the Bohr atom, we talk in terms of orbits, right? Those nice little rings we used to put the dots on. And an orbital is an extension of that idea, but it contains all of these special properties of the quantum mechanical atom. And it's this idea of the orbitals that really allows chemists to have a firm understanding of all the properties of compounds. So the quantum mechanical theory is such a good theory. It's an atomic theory, kind of like the Bohr atom, except like, you know, on steroids. And so it's an atomic theory, but this theory can be used to explain shapes of molecules, three-dimensional shapes. We'll be talking about that. Once you have the three-dimensional shapes of molecules and you introduce something called like polarity, and you've heard of polarity before, polar bonds, then you can take those shapes and you can describe intermolecular forces. We talked about that last year, and we'll be talking about it again this year, except in more detail. Those are the forces between adjacent molecules. And once you have intermolecular forces, you can then explain successfully properties of matter in terms of boiling points, melting points, solubility, all kinds of different properties, the way light is transmitted through it, et cetera, et cetera. So the quantum mechanical theory, even though it's quite a confusing theory and it's very difficult to understand, is a super powerful theory that explains matter very well, all right? In terms of the difficulty to understand, I'm giving you guys just the kind of upper surface of quantum mechanical theory. If you want to continue on in university and study quantum mechanics, it is as fun as it sounds, because that's what I did. My third and fourth year chemistry, if you take chemistry at university, your first 2 years are kind of like general chemistry, and then when you get third and fourth year, you have the opportunity to kind of specialize in a particular, type of chemistry, and there's all kinds of different types. There's what we call physical chemistry, which looks at the physical properties of the chemicals. And then there's organic chemistry, which you've been introduced to if you've been taking biology. And there's inorganic chemistry. There's organometallic chemistry, which integrates metals in with organic compounds. An example of an organometallic chemical would be hemoglobin, which contains iron surrounded by this organic kind of shell, and you can go into all kinds of exciting things. Most of them involve labs and all this good stuff. But then there's quantum theory, which is where the chemistry geeks hang out. And when I say chemistry geeks, I mean like physics geeks, because quantum theory is literally the physics of the atom, all right? And so you take your knowledge of physics and you take your knowledge of the way atoms behave, and you put them together, and you start with the fundamentals of quantum theory, and you put them into this big mathematical machine. Okay, it's not really a mathematical machine, but it's this mathematical construct that we call quantum theory. And in the end, when you're done doing pages and pages and pages and pages of math, you get these neat things called orbitals. And that's what I'm going to introduce to you today. I had a fourth-year quantum mechanical course, and there was only 2 of us in the whole course. The craziest thing ever. That's how popular this is. But I think it's cool. Yeah, there was only 2 of us in it. The other guy that was in the course was in there because in fourth-year university, you also have to do a lab that's like a full-year lab. You actually work for a professor as if you're like a master's student, that type of thing. And the student that was also in this course of 2 took the course because he was working for the professor who was giving the lectures, so he felt he was obliged to take the course. He skipped it all the time. I sat there in the front of the room, built for 50 people. He'd hand me the notes. I'd be writing stuff down. He'd be talking and looking over me. Right? Any questions? Anything? All right. I'd have to like say, oh yeah. It was the bizarrest thing ever. Anyway, it was just crazy. But anyway, So I have a background in quantum mechanics, which is like the physics of chemistry, and it's kind of fun. So let's very quickly, and this is just for your information, it's on the page. Oh, forget those pages. That's the old textbook. I forgot to update those page references. So yeah, those page references are no good. But if you find chapter 2 in the textbook at the beginning, you'll find all this stuff in there, all right? Chapter 2, I'm pretty sure it's under. It might be chapter 3, somewhere near the beginning. I'll find it in a minute. I'll tell you what to write down. Okay, so this is just a super review of what we talked about in grade 11, going all the way back to the first idea of the atom. Again, Democritus, Greek philosopher, doing a lot of thinking. I told you a story about Aristotle. He believed that matter was continuous and there were no such thing as these small little indivisible pieces. Democritus believed they were. He used the term atomos, that meant indivisible, and really he didn't do any science to prove it. He just had an idea, and he used the term atomos, which is what makes him a rock star in atomic theory. That's why we talk about the guy. That's about it. So moving on, next we talk about Dalton. Again, Aristotle's ideas were so dominant that nobody even questioned them. So this idea of atoms really did not prevail until Dalton came along and proposed the atomic theory. He was essentially trying to explain why certain gases dissolve better in liquids than others. He felt it was the easiest way to think of them as tiny little pieces. And then from that, this idea of atomic theory came flowing out. They're identical. They have no features. Hence, we call them the billiard ball atom. It was essentially the beginning of what we consider to be atoms. Okay, so we jump ahead a handful of, well, no, not a handful of years, probably about 100 years. And we get to Thomson. Lots of science has been done at that point in time. We've had electricity being introduced into mainstream science, where chemists were zapping absolutely everything that they could find with electricity, and they were discovering that all matter contained these tiny little particles, and these tiny little particles were called electrons. Electron meaning tiny little piece of electricity, all right? And ultimately, a guy by the name of Millikan was able to determine the mass of these electrons and the charge on them, which is very important. And really, this discovery of the electron is the beginning of something that we call in chemistry and physics quantization, all right? With the discovery of that smallest little piece of electricity, which we now call the electron, even though there was an atomic theory, chemists and scientists and physicists still believed that electricity was like a flow of something, a flow of charge like water, and there weren't little pieces of it. With the discovery of the electron, this beginning of quantization, and we'll see it over and over again. Quantization simply means that things are made up of little tiny chunks as opposed to continuous flowing substance. So this is the beginning of our idea of quantization, bringing us to what we call quantum theory, all right? So Thomson realized that these little pieces of electron were, or a little piece of electricity were found in all matter, and therefore he simply put the electron into the atom. He didn't really know what it was in, so he put it in this positive gelatinous goop, I sometimes say, because they had to be easily removed from them. I like to think of it like Jell-O fruit salad that you get at Christmas, right? You can easily remove that maraschino cherry because it is the most important part of the fruit salad. We all know that. And it can easily be removed from that, just like the gelatinous positive goop of an atom. All right. So kind of interesting, but still not earth-shattering. All right. So our next guy is Rutherford. We talked about Rutherford last year. Now something interesting has also happened in between Rutherford's theory and Dalton's theory, and because I'm making movies of this, I'll just write this on the smartboard. And I mentioned this to you last year, that at approximately 1900, actually it's exactly 1900, I don't even know why I put approximately, guy by the name of Max Planck, all right? And this is very important. It doesn't have to do quite yet with the atomic theory of Rutherford's, but it does have important kind of ramifications when it comes to entire quantum theory. What he proposed, what Max Planck proposed, was that light is not continuous, all right? The behavior of light and the behavior of matter was starting to really come together, all right? Up before 1900, well, around 1900, there had been some experiments done before 1900 where light was interacting with matter, all right? There was something called the photoelectric effect. We all know today something similar to the photoelectric effect. Essentially, if you have a solar-powered calculator or any solar-powered device, you all know that light energy comes in, interacts with that little solar thing, and it makes electricity flow, right? Electricity is moving electrons. That's matter. That's material substance. Light coming in are light waves. That isn't matter. That's light. It's light energy. And so at a little bit before 1900, scientists were looking at something called the photoelectric effect, which is really the youngest infant version of a solar cell, where light was coming in and ejecting electrons and causing electrons to flow. That was our first really look at the interaction between light and matter, that light was actually interacting in such a way that it was making the matter move, all right? It was making it do something. And the only way to really explain the photoelectric effect, and Max Planck didn't do this, actually Albert Einstein successfully explained it, but he used Max Planck's idea. Max Planck was explaining something else. It doesn't matter what he was explaining, but he was stating that light, all right, is made up of tiny little pieces or particles, all right? Little pieces or particles of light, all right? Before this, scientists thought light was continuous, a wave that just extended on from the light source to whatever it went to. But Max Planck realized that they had to be thought of as little pieces of waves traveling along, all right? And Planck called them quanta to represent little pieces of light. That's where our name for the quantum theory comes from. Quanta representing little pieces of light. Einstein came up with another name for it. Einstein called these little pieces of light photons. And I'm sure you've heard the term photons before. At least I hope you have. So photons or quanta are essentially little pieces of light. And all light behaves this way. Light is actually made up of tiny little particles of light. All right? Now that's an important part of our story, which we will come back to in a moment. I just wanted to stick it in because it was in 1900 that this idea was proposed. So let's head back to our atomic theory. 1911. I've told you this story before as well. Scientists like the Curies were studying radioactivity. They didn't discover it, but they were studying it. And Rutherford was also studying radioactivity. I don't know if you recall, but he came up with the terms alpha, beta, and gamma, which essentially means A, B, and C, right? Not very bright, well, he's very bright. Rutherford is a very bright man, but not very creative when it comes to naming things. And if you recall, he took alpha particles, and this is a simulation that doesn't work on our new PowerPoint, so I can't run it, but he essentially took alpha particles, which were small, tiny pieces, and he had them fire up against, and let me see if I can draw this on here. He had them run up against the nucleus, and they would be deflected away, and I don't know why that disappeared. Let's try that again. They'd be deflected away, and that's going to disappear every time. That's kind of bizarre and concerning. All right, that's fun. It must be because this is a simulation. But they were deflected away, and they would cause the screen to glow, and they would deflect back, and they would sometimes come straight back, and in the end, he concluded that there had to be something very small, very heavy, right? Most of the mass is in the nucleus, and something very positive. And so what did Rutherford do? He essentially discovered the nucleus. Didn't really comment on what was happening to the electrons outside of the nucleus, but in the end, Bohr took care of that. But there were definitely problems with having to explain the electrons. So again, this is right on your note. Atoms composed of equal number of negatively charged electrons and positively charged protons. Most of the mass of an atom and all of its positive charge are contained in the tiny core called the nucleus. The nucleus of an atom contains protons and neutrons that have approximately the same mass. 1U, again, James Chadwick discovered the neutron. Not a big deal. We're just reviewing from last year. And the very small, about 0.0005 U, right, in terms of their mass units, about 1/2000th negatively charged electrons occupy most of the volume of the atom. And we call this sometimes a solar system atom because we've got electrons kind of whizzing around wherever they want, kind of like how planets can whiz around wherever they would like, all right? There's no restriction on where the electrons can be. Okay, and that's just a little review of our fundamental particles. Again, this is on there. So we've got the protons, +1 charge, electron, -1 charge. They cancel each other out completely. Protons and neutrons have the same mass. They're heavy. They're found in the nucleus, and the electrons orbit the nucleus. And that's that. Again, just a quick little review of things like atomic number and mass number, because when we start building our atoms using the new quantum theory, we have to recall how to find all that good information. I don't think it's too groundbreaking. The big numbers, right, are our atomic numbers. That's telling us how many protons are in the nucleus, and it also tells us how many electrons are in a neutral atom. Mass number, we deal with that all the time. Remember, that's the sum of the protons plus the neutrons. But to be honest, in this unit, I don't care about the neutrons at all. I'm not going to be testing you on isotopes or weighted atomic average, all that good stuff we did last year. I'm just worried about protons and electrons so that we can build our atoms. We're not going to worry about the neutrons. Okay? And again, there's our good little atomic notation. Again, just a review, just to get it back in your mind, but I won't be testing you directly on this stuff. But, you know, we've got sodium-23 or Na-23, so sodium being the element symbol, which also corresponds to the atomic number, 11, and then obviously the mass number. And from that, we could determine the number of protons if we would like, but I'm not that concerned at this point. Just to review, isotopes, right? If they've got different numbers of neutrons, same number of protons, then they are isotopes, and the mass on our periodic table is a weighted average of all of the isotopes for that particular element. And again, and you know what? This textbook reference is wrong because I haven't changed these textbook references. But don't sweat about this. By the end of the class, I'll go through the book and see if there's anything important that you need to know. But you don't need to worry about that stuff. So there we have our different, so cross out those textbook references. I'm pretty sure they're old. Okay, so let's get to the good stuff, the stuff that I'm really worried about. And that is problems with the Rutherford model, all right? Number one, the nucleus should fly apart. It contains a whole bunch of positive charges. They should be repelling each other, and those positive charges should just take off all over the place. So Rutherford hypothesized the existence of a force that exists in the nucleus that holds them together. He called it the nuclear strong force, again showing Rutherford's great ability to name things. And therefore, and we now know and we've measured the strength of this force that holds everything together. Electrons are in motion around the central body. They must an electron in motion around the central body must continuously give off radiation. I would have described this to you last year by talking about wiggling that ebonite rod and producing light. I would have made a discussion. I don't want to go into it in depth because we want to get to the quantum stuff. But if you do recall, if we have any charge that is accelerating like an electron going around, that should be giving off energy, and that should be spiraling into the nucleus, and therefore atoms shouldn't exist based on that information. And so there's a problem with having just the electrons zinging around. I don't know if you recall, but we called this classical physics, right? I used what I didn't use it, but Bohr and the rest of the scientists would have been trying to explain the atom using physics that existed before 1900, and it was not satisfactorily explaining the atom. All electrons should be collapsing. So we should see a continuous spectrum, all colors of the rainbow being given off as it crashes in, all right? So they should spiral in and destroy the atom. And that is not the case. So what did Bohr do? Well, Bohr introduced something called quantization. Again, there's that word, quantization, or quantum coming back in. He introduced quantization for the orbits. Now, we say that the energy levels are quantized, all right? They have particular values of energy. The first orbit has a certain energy. The second orbit has a certain energy. The third orbit has a certain energy. Now, I just want to clarify that this energy, he didn't sit down one day and just say, I think there's orbits. What he did was he had to kind of work backwards, looking at the color of the light that was given off in the hydrogen atom, looking at this new idea of photons, doing some mathematics, figuring out how much energy was given off, and in the end, what he had to conclude, so here we've got Bohr, what Bohr actually quantized was what we would call angular momentum, all right? Quantized angular momentum, all right? Now this is more detail than I normally give. Don't write the rest of the equation down. You can write down quantized angular momentum. But because I know that there's a large group in here that takes physics with Mr. Petrus, I'm giving you guys a little bit more of a background here, because you have some background knowledge. You guys know what momentum is if you've taken physics with Mr. Petrus. What's the equation for momentum of an object? The simple equation to calculate the momentum of an object. P equals, mv, the mass times the velocity, right? If you want angular momentum, anything that's spinning has angular momentum or spinning momentum. It's displacing an angle as it goes around. So a figure skater, as they go into a spin, has angular momentum, all right? So he wanted to quantize the angular momentum. He used an equation that looked like this, mvr. Now, what r is the radius of the electron going around the orbit. That's how you calculate an angular momentum. You introduce its radius from the center of spinning. So mvr, he let be equal to a special series of numbers, nh over 2 pi. All right. Now, the 2 pi comes from the fact that it's going in a circle, and this h here, and you will talk about it in physics later on, is called Planck's constant. And it is named after Mr. Planck that we just saw up above. He actually came up with the energy for light using this Planck's constant. So Bohr realized that they had to spin, but they couldn't, they had to orbit, but they couldn't orbit in any particular fashion. They had to follow that equation. And if you, at the end of the physics course, Mr. Petrus will go through using this equation along with some centripetal motion equations, right? You guys have already done that type of thing, right? I'm trying to think what it is. What's the centripetal motion equation? What's the acceleration? Centripetal acceleration. mv squared over r? mv squared over r? There's a pi in it too. I haven't taught it for a long time. Anyway, you guys have a centripetal motion equation. You're going to find it for me. This is fun. Centripetal motion, centripetal acceleration.
4 pi squared RF. Oh wait, never mind. That's M.
I don't want that one.
M 4 pi squared and R over 2 pi.
Yeah, you could use that one. Really, you don't have an mv squared over r is the centripetal acceleration, right? Yeah. mv squared over r equals a, right? And you'll notice we got lots of m's and lots of v's and lots of r's, so it's really simple to put this into here. And you'll also use the equation that represents the charge, the force on charged objects. Have you guys got to electrostatics yet? No, you're just starting electrostatics? Okay, so you'll use some equations from electrostatics, and you'll put it all together, and what you can eventually get is the radius of the nth orbits. You can figure out the radius of all of the orbits just like Bohr did. And they work out very nicely. And then you can figure out the energy of all the orbits. And then you can do the calculations that Bohr used to do, and lots of other students did, to figure out exactly what the colors of those particular photons are when electrons jump up and down. So in the grade 12 physics, you can do the same mathematics that Bohr did to figure out all these orbitals. And it's kind of cool. It's very simple mathematics, but the main thing is right here. This is the chunk that was groundbreaking, the quantization of the angular momentum. In other words, you can have this spin, and you can have this spin, but you can't have the thing in between. You can only have certain allowed states, allowed places. And that's what really was groundbreaking that Bohr introduced, and we call that, again, it's a type of quantization. We're only allowing certain quantities. That's kind of neat. So, Bohr's model, protons and neutrons found in the nucleus. Here's the groundbreaking thing. Here's his introduction. The electrons occupy specific allowable energy levels called energy levels. That's fun. I like that line. Or stationary states, which correspond to a fixed circular orbit around the nucleus. Okay. So he's introduced energy levels. They come from quantization of the angular momentum, but mathematically, in the end, you get energy levels. And you guys know that. You guys know that the energy levels are there. Electrons typically exist in the ground state, closest to the nucleus. Energy can be, an electron can change energy levels by emitting or absorbing specific quantities of energy, called a quantum of energy, or a photon. So if a photon comes, it can cause the electron to jump up. When the electron falls back down to its orbit, it gives off that light in terms of another photon, all right? Electrons do not radiate energy when they're in an energy level. So if they're orbiting, they don't give off energy, and that breaks the rules of the old physics. An orbiting charge should be giving off light and should be crashing into the nucleus, and Bohr simply states, but it doesn't, so it mustn't. It just doesn't do that. And that was kind of where this new theory is like, what? Well, if it doesn't, then the physics of little atoms must be completely different than the physics of big charges that we know about. So there's some new physics coming in here. And that's a big one. That's a big one where scientists have to do some thinking and figure out what's going on. An electron, if an electron absorbs a specific amount of energy, can jump to a higher state. When the electron returns to the ground state from the excited state, it gives off light corresponding to certain colors of the spectrum. Okay, that's just a little simulation. Again, that does not work on this particular version of PowerPoint, but I can give that the right color of light, and it'll jump to different energy levels, and then it would fall back down, and it would give off light. It's not that exciting. Now, successes to the Bohr atom. What was good about it? He offered a reasonable explanation for Mendelev's periodic table. We can get our 2, 8, 8. It doesn't really offer an explanation for what's happening in the transition metals, but it gets us a start. The periods in the periodic table result from filling the energy levels of the atom, right? So group 1, 1 electron in the outer orbit. Group 2, 2 electrons in the outer orbit, et cetera, et cetera. All right, period 4 has 4 energy levels, and when the period comes to an end, you then reload or you start the next energy level. And that's our good old Bohr diagrams. We're just loading it up, all right? So we get a kind of idea of the way the periodic table comes from the Bohr atom, but we still can't explain the transition metals. Again, the maximum number of electrons in an energy level when it's, what am I doing here? Maximum numbers of electrons in each energy level when it's the valence shell is given by the number of electrons in each period. All right. The last digit of the group provides the number of electrons in the outer shell. We know that stuff from last year. Okay, so we're getting there. We're getting to the new stuff. Problems with the Bohr atom. He really could only explain mathematically one electron system, a nucleus and a single electron. Do the mathematics I've been talking about, get some nice orbits. Get the calculations that give you the orbits. It didn't have to be hydrogen. It could be helium +1, if you could remove an electron. It could be lithium +2, beryllium +3. Only things that had one electron could be explained. As soon as the second electron came in, the calculations were wrong, so it wasn't very good. He could only explain the number of spectral lines produced by, he could not explain the number of spectral lines produced by multi-electron atoms. So once other electrons came in, he couldn't explain those colors of light like he could for the hydrogen atom. He really could only explain the hydrogen atom itself, which, if you think about it, is not that great of a theory, right? The theory really could only explain the simplest atoms. So what are you going to do? Because most atoms have lots of electrons. Okay, so now I need to introduce you to some weirdness of quantum mechanics. Up to this point, even though some of you are starting to snooze, and that's the way it goes. I know the way this lesson goes. I know the way it works. That's the way it goes. It's a lot of talking. Even though I've introduced you to this idea of orbits, to say that the angular momentum is a particular value, that's not too crazy, because he really just made the mathematics work. I guess this is the weirdest thing. If the laws of physics state that an accelerating charge should give off energy and crash into the nucleus, yet it doesn't, we need new physics. We need new laws of physics to explain what's going on. And it was, yeah, we're not going to worry about that because I already talked about Bohr. It was this guy that really revolutionized everything, all right? He theorized that electrons behave both as a particle and a wave. Here's what he did. I introduced you to Planck. Planck in 1900 said, you know what? In order to really make the mathematics work and make everything follow what we see, I need to make light, instead of a continuous wave, I need to make it up in terms of little tiny pieces or particles. And it works to explain everything very well. Then Bohr started to talk about these orbits and started to talk about quantization. So there were all kinds of little equations around that were explaining electrons in atoms and light particles, and stick an E equals mc squared in there from Einstein, which related mass to energy. And so what Louis de Broglie did, he wasn't even a professor at the time. He was really just kind of working on his doctorate. And so what he decided to do was take all of those equations that seem to be talking about different things and imagine, what if they're talking about the same thing? So he essentially asked the question, okay, if light that we thought was a wave can behave as a particle, like a piece of matter, then maybe particles, which we know are particles, can behave like a wave. Why don't we just take the whole thing and turn it on its head? If light waves are now going to behave as particles, then why can't particles like electrons behave as waves? Things made of matter, material, now having a wave property. And what he did was he rearranged a bunch of equations, and in the end came up with an equation that related the momentum of a particle with a wavelength. There's the equation right there. This lambda right here is a Greek symbol. It means wavelength, and it says is equal to h, which is Planck's constant again, over mv, its momentum. So he's saying that anything with mass that's moving with a speed behaves like a wave. Right now, as I walk across the room, if I put my mass and my velocity into that equation, a wavelength will be calculated. I will actually have waving properties. Now, the wavelength in that equation for my body is phenomenally small. So the waviness is smaller than the defined edges of my body, so you don't see me disappear, do this type of thing across the room and reappear across the room. Because my wave properties are so tiny compared to the doorway and everything else, you don't see my wave properties. But if you calculate the wavelength for an electron moving at the speed it moves in an atom, you get a wavelength that's about as big as the orbit. So here's what he proposed. What we have now is, instead of electrons in orbit moving, they're not particles moving, but they're waves waving as they're in orbit. Now, what would that look like? Well, it would look like this. If I have the first orbit, all right, and you can add this to your picture. This is exciting. I'm going to put a dot there. I'm going to put a dot here. I'm going to put a dot here. And I'm going to take a wavelength like this. That is one wavelength. It consists of one crest and one trough, for those of you who maybe haven't taken physics. All right? And I'm going to take that wavelength and I'm going to wrap it around the orbit itself. So if this is the first orbit with the nucleus in the middle, this electron in the first orbit will wave around like this. Now you might think that that's just an offset circle, and it does look like an offset circle. But as it continues to wave, this outer part is going to become an inner part, and this inner part is going to become an outer part, just like this wave is going to go like this, and crests are going to become troughs, and troughs are going to become crests. This thing's going to go like this, and it's going to wave. When a wave stands still and you get a good wave forming like this, I don't know if you saw that. I don't have something to demonstrate a standing wave. Do you remember standing waves from physics, where you'd wiggle it back and forth and it would just kind of stand there and do that funny thing with your eyes? You could just see those loops. Remember they called them loops and nodes, right? Loops and nodes. That's fun stuff. That's exactly what's happening to an electron in the first orbit. It's not actually a moving electron because it's a standing wave. That's why it doesn't radiate energy, because it's not really orbiting. It's just a standing wave. We've got two nodes here, and we've got two loops here. In the second orbit, we're going to have two wavelengths. Crest, trough, back to a crest. And in the second orbit, it waves with a higher, faster moving standing wave with more loops and more nodes. And if you recall playing with the springs in the hallway, because everybody gets to play with the springs, if you want to make more loops, how do you have to move the spring? If you want to make more of them, you got to move it faster. And I always tried to get 8. Did anybody get 8? No? You try wiggling that thing like crazy, trying to get 8? Think about the amount of energy it takes. The more loops and the more nodes, the more energy, the higher the energy of the electron. N equals 3. 1, 2, 3, 4, 5, 6. Crest, trough, crest, trough, crest, trough. 3 wavelengths. What if you tried to stick 3.5 waves on it? What if you tried to stick an orbit where an orbit shouldn't be? Well, let's try it. If it's 3.5, I'm going to have 1, 2, 3, 4, 5, 6, 7 dots on this circle. 1, 2, 3, 4, 5, 6, 7. And if I try to complete the wave for this, crest, trough, crest, trough, crest, trough, crest. Now look at what happens. Now I've got a trough on a crest. What do we call it when you have a trough and a crest at the same spot? What happens to the wave when you have a crest and a trough at the same location and they're the same size? Yep. It cancels it out. Anybody remember what that was called? I call it TDI. TDI stands for total destructive interference. It means that if an electron tries to exist in between orbits, it won't. It cannot exist in between orbits. It cancels itself out. Remember how last year I talked about how an electron, maybe in the first orbit, was trying to go to the second orbit, how it actually disappears and then reappears in the second orbit? That's because it physically cannot exist in between orbits. If it's existing as a wave on a circle and it tries to move to the next number of loops and nodes, as it goes through there, it actually destructively interferes and then appears in the next level. It would be kind of like if you're doing the spring experiment where you're at 2 and then you want to turn it to 3 loops, you wiggle your arm a little faster and then something goes goofy with the spring and then all of a sudden, boom, you've got 3. Wiggle it a little faster, bang, now you got 4. That's what an electron jump is like. You come in with a little bit of energy, it makes the electron wiggle a little faster, and boom, it now has 2 waves, and it's jumped to the second orbit. Now, this is what we call the wave mechanical model, because it's based on waves, but it's not what we actually think of. Because the question was, if electrons are waving, then what does the waving really mean? What does that waving mean? And that was a difficult question. Let me show you one thing here for a moment to try to talk about what the waving actually means. I'm going to switch this. No, we'll leave this right here. What I have here, a little demonstration, and it's got a little laser on it, so I'm going to try not to get Caitlin right in the eye, so we'll move down here. So, laser beam, all right? Very straightforward. See there on the back wall? We'll turn off some light. Okay? So, here we got a laser. And I'm going to take this light. This is a light wave. This is not electrons. It's a light wave. And I'm going to take this light wave and I'm going to shoot it through some slits or some openings. There, I've got it right there. All right? So that is a single light wave going through some slits. Now, hopefully you can see that there's a central bright dot. All right? And then the dots fade off as you go to the side. Okay? Now, this experiment was done in the 1800s by a scientist by the name of Young. And in Mr. Petrus's class, you're going to talk about Young's double slit experiment. And that's just exactly what I've demonstrated to you, Young's double slit experiment. And just to kind of give you a little drawing representation of it, and you don't have to draw this, but in Young's double slit experiment, he takes some light, all right? We'll take a laser beam. He takes some light and he puts it through 2 slits. And what happens is the light waves interfere with each other and they make varying brightness and darkness amounts. So this represented bright, all right? This big peak there represents the bright dot at the back. And for light, what it did was it caused some wave interference, and you'll learn more about wave interference. You may have already talked about wave interference. Those waves overlap and they interfere, and it makes it bright. All right, and you'll learn about Young's interference when you get later on in light and waves after electromagnetism. So they did that with light. So it didn't take long for scientists to say to de Broglie, "You're telling me that electrons behave as waves? Then what if we took Young's experiment and instead of taking light, we took an electron beam, electrons. And we shot those electrons through a double slit, just like light through a double slit. If they're behaving as waves, then are you telling me that we should have a bunch of electrons smeared along here like a bunch of dots in this experiment? Here's what they found. As they let this experiment run, they found the detector that could detect electrons were starting to get spots on it from each electron running into it. And in the end, they got a pattern that looked just like the wave pattern. But in the end, it wasn't light waves that were striking them. It was still the electrons themselves. So it's not that the electrons themselves were waving, but something was waving, and what they determined was waving, and this is what they mathematically calculated. Can't spell probability. Did I spell probability right there? I had to say it. What they determined was the waving is a wave of probability, a wave of where you will most likely find the electron. They even did the experiment in such a speed that it was calculated that only one electron was going through the slits at a time. And scientists said, so which slit did it go through? The top one or the bottom one? And they said, I don't know. But when we do it, we get the same pattern as we do for the light. And then you know what a scientist did? They just, all right, if there's only one, let's cover up one of the slits. And what happened was this entire pattern disappeared, and they simply got a whole bunch of electrons as if it came right through the slit. So as soon as you covered one slit, the wave property disappeared. As soon as you took your finger off the other slit, the wave pattern came back again. So where's the electron going? Is it going through one slit? Is it going through the other slit? Is it somehow simultaneously going through both slits? There's all kinds of different theories on what it's doing. Many scientists don't even know, but we just know it does. And we know mathematically we get areas of high probability where we will most likely find the electron as it goes through the slits. So what we now know is that electrons, they move with this waviness of where you're most likely going to find the electron. That's exciting stuff. That's kind of weird. That's weird physics. That's what that is. So let's go back and talk about a couple of other people, and I'll talk about what this means. Actually, I'm going to jump ahead and talk about Heisenberg right now. You guys are going to be all, the Heisenberg, those are my Heisenberg animations, and you're all going to be kind of mesmerized by them. Good, I hope they stop. Heisenberg took this idea of probability, did a bunch of mathematics, and realized something about the incredibly tiny when it comes to electrons, protons, and neutrons. He realized that when you go and look for an electron, let's say you're going to go and look for an electron in an atom somewhere. I know there's electrons in that hydrogen atom. I'm going to go look for it. When you go and look for an electron, there's a limit to how much information you can know about that electron, and it's mathematically proven. The more precise you know the position, if you know where it is, you really don't know its velocity very well. Its velocity is related to the energy. So if you know where it is, you really don't know how fast it's going. But if you then change your experiment and figure out what its speed is, you might know its energy. You really don't know where it is. Now, what does that mean? If you can't know both of them very well, and you want to think of a Bohr atom, essentially, if I say that this is n equals 2, the second energy level, and I say it's got to be right there, and I say because of my mathematics I can determine the speed, then I'm breaking the Heisenberg uncertainty principle. It's a very well-known law. What that means is, if I'm talking about n equals 2, as the energy, then I really don't know its position very well. So in n equals 2, the electron isn't going to be on that circle anymore. It might be just outside the circle. It might be just inside the circle. There's going to be a high probability that it's going to be close to the circle, but it might be way out there. There'll be a low probability that it's way out there. And it could even be way in here. The n equals 2 electron could be right in close to the nucleus. Low probability of that as well. But the mathematics shows that we don't know that there's exact orbits anymore. We just know that there are these spaces. Can I stop? Okay. We just know that there are these areas around what we thought were the orbits that are really just areas of where we're most likely going to find the electron. So what is our new view of the atom? Our new view of the atom isn't nice, definite circles where we say the electron is there. Our view of the atom is we've got these areas where we now know that the electron might be based on its wave of probability. All right? So we now don't have a for certain knowledge of where the electron is. We only really know where the electron might be. Okay? Now this thing on the Zeeman effect, this was an experiment that was done that looked at the spectral lines, put it in a magnet. This B means magnetic field in physics terminology. And when you put the atoms in a magnetic field, you put a big magnet around it, the lines that were in the colors split into 3. Some split into 5. Some split into 7. It was very distinct. There was either no splitting, 1. There was either a split into 3, or a split into 5, or a split into 7. What that concluded was that our orbits are not made up of just single levels, but there are these sublevels in there. That there are sublevels with different orientations. In other words, we now don't have nice rings, but we have some of them that have 3 sublevels with 3 different orientations in space. Probably one up, one out, and one, perpendicular to it, X, Y, Z. But then there was some that split into 5, which means that orbit had to have 5 sublevels with 5 different orientations in space. So now our nice rings, which have turned into now these fuzzy rings, which are now being turned into 3 separate things that are perpendicular to each other and are fuzzy. So now our atom is really taking on a different shape. And that's what I have to teach you. What are these new shapes and how do we think about them? All right, we're almost there. This is exciting. I have hardly any sleepers going on here. This is good. So we got a fuzzy atom now, and we got a fuzzy atom with all these different shapes. Look at, you see, Heisenberg. He's either a particle or he's a guy, right? Anyway, okay. Last guy, last name, the last name drop. Schrodinger. Schrodinger and Heisenberg were contemporaries. Actually, right here, right? There's Heisenberg. There he is. And there's Schrodinger. See? All these guys. And look at de Broglie. He's a little weasel in the middle here with his little wave mechanics. Right there, de Broglie. You can take a look sometime. I've got it online. I'll put it on the website. This was a meeting of quantum. This was a quantum mechanics thing. There's a lot of heavy hitter physics and chemistry here. We got Curie and Einstein in here. A Bohr here's hiding over here. Anyway, all right. So Schrodinger, about the same time as Heisenberg. Heisenberg did his calculations to figure out the uncertainty principle using something called matrix mechanics or mathematical matrices. Do you guys do matrices in math anymore? We used to do it in a grade 12 course. A matrice is a great big set of brackets with all these different numbers, and you can multiply the matrices through, and you can do all these crazy things. Schrodinger didn't use matrices. He used calculus, all right? And it's really quite a complicated thing. Now, what Schrodinger proposed was something called the wave equation, all right? Schrodinger's time-independent wave equation. And when I took my quantum mechanics, that's the first thing you learn is the wave equation. And then you start by building your atom, putting it in, we say put an electron in a box. Now, an electron in a box is just a saying of saying putting electron in a space that it can't leave. An atom, a hydrogen atom, is essentially putting an electron in a box because there's this positive piece and it can't escape from that pole. So we do the calculations for an electron in a box. And then we expand our knowledge to change the box that make it look more like an atom itself. And then you do lots of mathematics. And then for your final exam in fourth year, what you do is you're given the starting point, Schrodinger's wave equation. You take all of the physics that you've learned, you put the electron in, you do about 4 or 5 pages of calculus and calculations. About 80% of it I've memorized because I really didn't understand half of this stuff. About 20% I knew the little steps. And you give them back what you want, you get 90%, and you really didn't learn a whole lot of quantum mechanics, even though I got 90% in the course, right? Because I could memorize my way through it. But I did learn little bits and pieces of it. But when you do this, and you do all this mathematics, and you come out with this equation that has certain numbers in it, certain constants, there's an N in it, there's an L in it, there's an M sub L and an M sub S. So everything else is a whole bunch of constants, and then there's these 4 variables. And this equation that you get is what we call the wave function, all right? And that wave function, again, describes the probability of where you will find the electron. So it's this big mathematical thing that doesn't tell me where the electron is, but it tells me where I'm going to most likely find the electron. The amplitude of the wave function tells me the probability. If it's a big amplitude, a big wave, there's a great probability of finding that electron in there. Each wave function gives me information about the energy and location of the electron within the atom. These 4 special numbers, we call them quantum numbers. They describe all of these new things that we're calling orbitals. So now we're going from orbits to fuzzy orbits to doing lots of mathematics that gives us the wave function that has 4 unknowns in it, that when we substitute numbers into these unknowns, we generate these shapes that we call orbitals. And we now think that the electrons exist in these orbitals. They have a high probability of existing in these orbitals. All right, we're almost there. Question, I got a question that's exciting, yes? Yes. Of the velocity? That's correct. So again, it's a probability of energy, and it's a probability of location. So we can never say it exists there, but we can say that it's going to exist in this space with a 95% probability. And the electrons that exist in that space will have this energy with 95% probability. It's not accurate, but it's as good as we can get it. And that's what we've got to settle for when dealing with quantum mechanics. You can never know exactly. You can just know about, right? Depends on what your tolerances are. Great question. I've never had a question with this lesson. Okay, so let's finish off talking a little bit about orbitals. This is the key to this entire unit. I'm going to be showing you right now some shapes of these orbitals. On Monday, I guess after the test, I'm going to talk about these quantum numbers that are going to define these orbitals. We're going to learn the shapes of the orbitals, and then we're going to start putting electrons into the orbitals, and we're going to start building our atoms. And we're going to get their 3-dimensional shape. Then we're going to bring atoms together, and we're going to have orbitals overlapping and creating bonds. We now know that bonds are formed when 2 orbitals have an overlap. And because they're waves, when you overlap orbitals, it's just like mixing waves together. It's like music. Good, eh? See, I made a little link with music there. That's cross-curriculum right there. Anyway, so you overlap them, and you can overlap them just like any waves. You can create bonds. Okay, so what is an orbital? And this is where you really have to pay attention up to this stuff, right? It's a 3-dimensional region of space around the nucleus where we have a probability, and we define it as chemists 95%, we're going to say 95% of the time the electron is going to be in this space. That's good enough for us of finding the electron. Each orbital has its own associated energy. The concept of electron probability leads to the idea that electron behaviors, that the electron behaves as if it were spread out around the nucleus. So we don't now say that the electron is there or there. We say that the electron is 95% of the time going to be in here, and we really don't care where it is. It's like we've got that negative charge and we've kind of spread it over this space. Sometimes it's called an electron cloud, but it's only made up of 1 or 2 electrons that are either here and 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 here. But because they're moving and doing this thing, they're kind of in this space. So we really don't worry about where the electrons are anymore. We just think about where we're most likely going to find them. All right. Let's not worry about this because I'm just getting to the time here. This describes a summary of the quantum mechanical view, but I do want to jump to the end. This is not a bad thing to kind of read through, but I want to jump to the orbitals here. Now, your picture isn't that great, but we will be seeing these shapes over and over and over again. No need to draw them. I'll draw them a little later on as we do them. The simplest orbital is called an s orbital, all right, S. You might think it comes from spherical because it's a sphere. That's kind of a neat way to remember. But the S actually comes from sharp because it came from those spectral lines. And the S was the one that stayed as 1. It's sharp. It didn't split because of the Zeeman effect. The next type orbitals are called p orbitals. Can't remember why they call them p orbitals. They're the ones that split into 3 because there are 3 distinct orbitals that have orientations all perpendicular to each other on the x, y, z axis. The distinct property of the p orbitals is that each orbital is made up of 2, we call them lobes, like earlobes. So each p orbital is made up of 2 lobes, and each of these orbitals, each one of them that I'm describing, holds 2 electrons. All right, we would have saw that in the summary, but I'm just going to quickly explain, and I'll talk about that more later on. So 2 electrons can go in this S, 2 electrons can go in this px, py, 2 electrons, pz, 2 electrons. Each orbital can only hold 2 electrons. So we think of electron pairs existing 95% of the time in this space. The next type orbitals are d orbitals. You'll notice they now contain 4 lobes. The number of lobes increases. This picture and this, they're literally waves that are kind of being drawn on a 360-degree rotation. That big equation, all right? We don't think of it as a wave like this now, but, you know, it goes out and in and then out and then in, right? We actually had to draw these by hand on polar coordinate paper. Yeah, it was painful, very painful. Here, as you go through 360 degrees, this goes out and in and out and in and out and in and out and in 4 times. These are d orbitals. Again, don't worry about what the d stands for. I can't even remember what it is. They're just that's what we call them now. So we've got s orbitals, 1, p orbitals, 3, d orbitals are 5. These look pretty similar, and then there's this goofy one. And it's just the way it is. It's just the way the mathematics determines what it is. There are f orbitals, there are g orbitals, there are h orbitals, and as you can imagine, the complexity grows with each next level of orbitals. In this course, we will only be dealing with s, p, and d orbitals. I will be mentioning f orbitals, but we won't be doing any calculations with them or anything like that. Not that we do high calculations, but I mean solving problems with it, okay? All right, that is fun. Let me just go back here just for a moment, because I do have the time. So, these orbitals, each energy level contains sublevels of slightly different energies. And that S and P and D are the sublevels. And I will go into greater detail of this in the future. I'm just introducing it. Each sublevel contains orbitals. Each orbital can hold 2 electrons that spin in opposite direction. and each orbital is associated with a particular size, a three-dimensional shape, and an orientation around the nucleus. Okay, so I don't have a picture representing this, but if I've got something like zinc, zinc has to use the s, the p, and the d orbitals. So an atom like zinc would actually have an electron shape that takes this, superimposes it onto one spot, with the electron being right at the center of all these things, and then the electrons being put into those orbitals two at a time. And then we've got our atom. So it looks nothing like the Bohr's rings. It's got this shape to it. And now what we have to do, well, first I'm going to introduce to you how we come up with these shapes. Not with the shapes, but the numbers. And then we're going to talk about how we fill the atoms. And then once we've got the atoms filled, we'll talk about how they bond together to form ionic bonds and covalent bonds. And at this point, it goes through just like our first unit did kind of in grade 11. Now that we've defined the atoms, we can talk about atoms, ions, and bonding. And that's where the unit goes from here. All right? Okay, I'm going to stop this recorder. Oh, I don't want to stop it here.